The world is entering a new era. An era shaped not by traditional weapons or political speeches, but by machines, algorithms, and microscopic circuits. Every country, every company, and every person now depends on a silent system hidden inside massive buildings, buried servers, and invisible networks. This is the chip war, a global battle for computing power, artificial intelligence, and control over the digital future of humanity. And very few people understand what is really happening behind the scenes. Artificial intelligence has moved from laboratories to everyday life at an unprecedented speed. What was once the domain of science fiction and specialized research has quietly, then suddenly, woven itself into the fabric of our daily existence. It's in the palm of our hand, the cloud above our heads, and the systems that power our world. This transition didn't happen overnight. It was the result of decades of research, punctuated by key breakthroughs that unlocked exponential progress. The modern AI era arguably began around 2012 with a pivotal moment in computer vision. An algorithm named AlexNet demonstrated a remarkable ability to recognize images, far surpassing any previous attempts. This victory, powered by a technique called deep learning and the parallel processing power of gaming chips, ignited a revolution. It proved that by training large neural networks on vast amounts of data, we could teach machines to perceive the world in ways previously thought impossible. In the years that followed, this capability expanded across different modalities. First came speech. AI learned to understand our spoken commands and reply in natural-sounding voices, giving rise to the virtual assistants now common in our homes and on our phones. Then, it mastered text. It learned to translate languages with stunning accuracy, summarize dense documents in seconds, and even write original prose, poetry, and code. Today, its applications are everywhere. It writes, designs, calculates, predicts, translates, and analyzes. In the consumer world, it recommends the next song on your playlist, filters spam from your inbox, and helps you navigate through traffic. It powers the search engines that answer our questions and the social media feeds that connect us. In the enterprise, AI is a silent partner in critical operations. It runs businesses, automates decisions, and powers entire industries. It optimizes supply chains for global retailers, detects fraudulent transactions for banks, and helps farmers maximize crop yields. It accelerates drug discovery in pharmaceuticals and creates personalized learning plans in education. Since 2022, the pace of change has become staggering. The advent of large-scale generative models marked another quantum leap. These are not just analytical tools, they are creative engines. AI models have grown thousands of times in complexity, measured by the number of parameters they contain, the internal variables that encode their knowledge. This explosion in scale has unlocked emergent abilities, allowing a single model to perform a vast range of tasks it was never explicitly trained for. The world's largest companies, Microsoft, Google, Amazon, Meta, and others, are now in a race to create systems that will shape the structure of global society. They are competing to build the most powerful, most capable, and most general artificial intelligence, what many call foundation models. These systems are poised to become the new platforms upon which future technologies will be built, influencing everything from commerce and communication to science and governance. But AI has a cost, a massive cost. This incredible progress is not virtual. It is profoundly physical, demanding immense resources from the real world. The computational power required to train a single, state-of-the-art AI model is astronomical, consuming as much energy as a small city over several months. And this is just the beginning. Training and running these models require supercomputers made of specialized chips, and the demand is increasing every single day. These are not ordinary computers. They are vast clusters of thousands, sometimes tens of thousands, of highly specialized processors known as accelerators or GPUs, all working in concert. Building and operating these AI factories is a multi-billion-dollar endeavor, pushing the limits of engineering and manufacturing. The demand for these chips is insatiable, creating a global bottleneck that dictates the pace of AI development itself. Because of this intense physical dependency, AI has become a global infrastructure. Just like electricity, water, or the internet, it is no longer just software. It is a utility, a foundational layer of the 21st century economy that requires a constant supply of power to generate intelligence. Its data centers need enormous amounts of water for cooling. Its models rely on a planet-spanning network of fiber optic cables to move data. The performance of an AI is now directly tied to the resilience and capacity of our planet's most fundamental resources. And behind every AI model, there is a supply chain most people never see. A complex, globe-spanning network of mines, refineries, chemical plants, fabrication facilities, and logistics networks. It begins with the extraction of raw materials like silicon and rare earth metals. It continues in the world's most advanced semiconductor foundries, where chips are etched with microscopic precision. It involves assembly, packaging, and shipping across oceans to be installed in colossal data centers. This hidden physical journey is the bedrock of the digital revolution. Understanding this supply chain is the key to understanding the future of artificial intelligence itself. For the first time in history, a technology is not replacing physical labor. It is replacing cognitive labor. Customer service, marketing, data entry, content creation, legal assistance, financial analysis, design, coding. Jobs once considered safe are now facing automation at scale. Reports from economic research groups estimate that hundreds of millions of workers worldwide may experience disruption in the coming decade. This is not a distant scenario. It is happening right now. As AI becomes faster, cheaper, and more advanced, the value of human skills is being redefined in real time. The global workforce is entering a transition unlike any other in the modern era. At the center of the artificial intelligence revolution is a single, indispensable factor: computing power. This isn't just about faster computers. It's about a new kind of computation, one that can mimic the neural networks of a human brain, but at a scale and speed we can barely comprehend. The engine driving this transformation is not the familiar CPU that has powered our digital lives for decades, but a new class of specialized hardware. The world now depends on these high-performance chips, accelerators and graphics processing units, or GPUs. Originally designed to render realistic video game graphics, their architecture proved to be perfectly suited for the parallel processing required by AI. These processors are the digital foundries where modern AI models are forged, handling trillions of data points to train vast, complex networks. Without them, the AI breakthroughs of the last decade would have been impossible. In this new landscape, one company, NVIDIA, has achieved a position of unprecedented dominance. It currently supplies the vast majority of the specialized chips used for training artificial intelligence. Its powerful software ecosystem, CUDA, created a deep competitive moat, locking developers into its hardware. As a result, its flagship processors, like the H100 and its successor, the H200, are in extreme, almost insatiable demand worldwide. They have become the most sought-after tools of the 21st century. But NVIDIA is not the only player. Competitors like AMD and Intel are racing to develop their own powerful accelerators. Meanwhile, the largest technology companies, Google, Amazon, and Microsoft, are designing their own custom silicon, or ASICs, tailored specifically for their AI workloads. This is a high-stakes race to control the hardware that will define the next era of technology. The scarcity and strategic importance of these chips have ignited a global competition. Governments see them as critical for national security and economic leadership. Corporations need them to maintain a competitive edge. Universities and research labs require them to push the frontiers of science. and military institutions are vying for them to develop next-generation defense systems, from autonomous drones to advanced intelligence analysis. Access to compute has become a primary measure of power. This competition is complicated by the chip's incredibly complex and fragile global supply chain. It begins with design, a process reliant on sophisticated electronic design automation, or EDA, software from a handful of American and European firms. These digital blueprints, containing billions of transistors, are the intellectual property at the heart of the chip. The blueprints are then sent to fabrication plants, or fabs. The world's most advanced chip factories, capable of producing chips with features measured in single-digit nanometers, are located primarily in Taiwan and South Korea. These facilities, operated by giants like TSMC and Samsung, are marvels of modern engineering and have become strategic assets of immense global importance. Their geographic concentration represents a critical vulnerability in the supply chain. Inside these fabs, the most crucial tool is the lithography machine, which uses extreme ultraviolet light to etch the chip designs onto silicon wafers. Nearly all of these machines are made by a single Dutch company, ASML. Control over the export of this equipment is a powerful lever of geopolitical influence. After fabrication, the chips undergo advanced packaging, a critical step where multiple chiplets are integrated into a single, powerful processor. This is another highly specialized stage, concentrated in East Asia. Finally, a global logistics network of cargo planes and container ships moves these finished processors to data centers around the world. A disruption at any point in this chain can have cascading effects globally. Recognizing this vulnerability, nations are scrambling to bring manufacturing home. The United States, Europe, and Japan are investing billions in subsidies to build new domestic fabs. Policies like the CHIPS Act, sanctions, and stringent export controls are being weaponized to protect existing technological leadership and to slow the progress of rivals. This is industrial policy on a scale not seen in decades. The competition, therefore, is not merely economic, it is fundamentally geopolitical. A new kind of great power struggle is unfolding, fought not with armies on a battlefield, but in clean rooms, boardrooms, and the halls of government. It is a silent, high-stakes conflict for technological supremacy. The reason is simple. Control over the supply of advanced chips means control over the development and deployment of artificial intelligence. And in a world increasingly run by algorithms, control over artificial intelligence means direct influence over the digital, economic, and military infrastructure of the future. The chip war is not just about silicon, it's about shaping the century to come. While chips are the brain of AI, data centers are the body. But this is no ordinary body. It is a globally distributed organism, a vast interconnected anatomy of steel, concrete, and silicon that forms the physical foundation of our digital world. This body requires a skeleton for structure, a circulatory system for power, a nervous system for data, and a sophisticated metabolism to manage immense heat. Without this physical form, the intelligence of AI would remain a disembodied ghost, an abstract potential with no way to interact with reality. These facilities are the factories of the 21st century, but instead of producing goods, they process the world's most valuable commodity, information. Thousands of these facilities are operating around the world, with hundreds more under construction at any given moment. They range from sprawling hyperscale campuses, some covering millions of square feet, to smaller edge locations positioned closer to urban populations. These digital fortresses are strategically placed, often in unassuming locations. Many are hidden from public view, located in remote regions, underground structures, or secured buildings with no external indication of their purpose. This secrecy serves multiple functions. It enhances physical security against threats, protects valuable intellectual property, and maintains the operational stability that our society now depends on. They are the invisible engines of the modern economy, storing our collective data, running the algorithms that shape our lives, supporting trillions of dollars in financial transactions, powering the apps in our pockets, and processing information for billions of people every second of every day. The lifeblood of a data center is electricity. Their appetite for power is almost insatiable. A single large facility can consume as much energy as a small city, and the industry as a whole accounts for a significant portion of global electricity consumption, a figure that is growing exponentially with the rise of AI. This is why their locations are so critical. Some are built near massive hydroelectric dams or in sun-drenched deserts to capitalize on renewable energy sources. Others are situated next to major power substations, tapping directly into the national grid. To ensure uninterrupted operation, they are fortified with layers of power redundancy. This includes uninterruptible power supplies, or UPS systems, which use massive batteries to bridge the gap of a few seconds or minutes, and colossal diesel generators capable of powering the entire facility for days or even weeks, guaranteeing the digital world never goes dark. All of that electrical energy ultimately becomes heat. Managing this heat is one of the greatest engineering challenges in modern computing. If left unchecked, the processors inside the servers would quickly overheat and fail. Consequently, up to 40% of a data center's energy consumption is dedicated solely to cooling. Traditional methods involve computer room air conditioning units, which function like massive, powerful versions of a home AC system. More advanced facilities rely on liquid. Some use chilled water that circulates through pipes to absorb heat, while cutting-edge designs employ direct liquid cooling, where dielectric fluids flow through cold plates mounted directly onto the hottest components, carrying heat away with maximum efficiency. This constant battle against thermodynamics is crucial for keeping the digital world running smoothly. If power is the lifeblood, then data is the neural impulse. The data center's nervous system is a web of fiber optic cables, capable of transmitting trillions of bits of information per second. Inside the facility, these cables connect racks of servers to each other and to the outside world. These connections are the physical manifestation of the internet, linking the data center to global telecommunication networks through vast terrestrial and subsea cable systems. Every email you send, every video you stream, every search you perform travels through this intricate network. The speed and reliability of these connections are paramount, enabling the near instantaneous communication we now take for granted. The promise of this infrastructure is continuous availability. To quantify this, the industry uses a classification system known as tier levels. A basic Tier Y facility has single points of failure, while a Tier Y4 data center, the gold standard, is fully fault-tolerant. It has multiple independent and physically isolated systems for power and cooling, allowing for maintenance or an equipment failure to occur without any interruption to service. This level of redundancy is non-negotiable for critical applications. If these systems were to stop, even for a moment, entire sectors would fail instantly. Airline networks, payment systems, communication platforms, emergency services, logistics, transportation, and even national security operations would grind to a halt. The complex choreography of modern life would simply cease. From the Arctic Circle to the desert, from subterranean bunkers to nondescript urban warehouses, this global network of data centers operates silently, 24 hours a day, 7 days a week. It is the largest and most complex machine humanity has ever built. The modern world relies on an infrastructure that most people will never see, a hidden anatomy that gives the digital age its physical form and enduring power. As AI becomes essential to global operations, the organizations that run it hold unprecedented influence. Major tech companies now manage cloud computing, digital communication, online commerce, and the core algorithms that shape global interaction. Their platforms connect billions of users, process trillions of operations, and sustain the digital economy. In many ways, these corporations operate like digital nations. They have infrastructure, budgets, global reach, research divisions, and the technological capacity to influence the direction of entire industries. Their decisions affect how people work, learn, communicate, and build businesses. Artificial intelligence strengthens this influence even further. The new centers of power are not physical territories. They are networks, chips, data centers, and digital ecosystems. The next decade will redefine the relationship between humans and technology. Artificial intelligence will expand into transportation, healthcare, manufacturing, energy, finance, and scientific research. Digital autonomy will increase. Data will multiply. New forms of automation will emerge. At the same time, the global demand for computing power will continue to rise, pushing nations and companies into deeper competition. The world is moving toward a digital structure where the ability to process information is the foundation of progress. Countries and corporations are preparing for a future where technological leadership determines influence on a global scale. The outcome of this race will shape the next era of civilization. Artificial intelligence is not only a tool, it is a new layer of global infrastructure. Chips, data centers, and digital networks form the backbone of modern society. They power economies, support communication, and drive innovation. The chip war is not just about technology. It is about the architecture that will define the future of humanity. The question is no longer whether AI will reshape the world. The real question is, who will shape the intelligence that will reshape us?